Welcome to the first lecture of module 2 of chemical reaction engineering 1. In this module we will discuss stoichiometry. So, before going to this lecture, let us have brief recap on our previous lecture. In our previous module, which we had in the 3 lectures in our previous module, the first thing we have considered introduction and overview for the chemical reaction engineering course. Then we have discussed the kinetics of the homogeneous reaction, where we have considered different mechanisms which may occur and what is their kinetics of the reactions, the order of the reactions, the molecularity of the reactions, and how to get the order of the reactions from a particular rate equations. Then we have classified the kinetics of the reactions into elementary and non-elementary reactions. Then we have considered kinetic models, that means rate equations, and how to obtain a rate equations from the different kinetic models, and how to test the models which we develop for based on some particular mechanism that we have discussed in the last lecture. And we have also considered the temperature dependency of the rate equations. That means the rate equations is a function of temperature and the composition. The temperature dependency term is related to the rate coefficient, and which is popularly well known equations which is developed is the Arrhenius equations of the temperature dependency of the rate equations, which we have considered, and we have seen for a particular reactions how to calculate the activation energy. Now, in this lecture we will consider introduction to stoichiometry, introduction and stoichiometry of the batch reactor systems. So, the brief lecture outline would be introduction to stoichiometry, why it is important and what are the things we need to take care while designing the reactor. Then limiting reactants, and then we will consider stoichiometry for the batch system. In most of or some of our algebra in the textbook is commit some common mistakes by treating chemical reaction as algebraic equations. That means, for example, if we consider nitric oxide reacts with oxygen and form nitrogen dioxide, and it is written like this, and then we can just take the twice NO2 on the left side, we can write twice NO plus oxygen minus twice NO2 is equal to 0. Whether this equation or these chemical reactions are correct, these two reactions, whether they are correct or representation are correct. As you can see, these are represented with the equality sign. So, chemical reaction cannot be represented with the equality sign. So, this is not correct. So, in some of the textbook you will notice like this equation do not make any sense mathematically. So, do not do this. So, while writing a chemical reactions, we must be careful that whether the reaction is irreversible in nature or reversible in nature. So, based on that we have to include this sign. So, we cannot use like a mathematics. So, like we have to write either this arrow forward or we can write the reversible sign. So, for chemical reactions this has to be represented with a particular notations. So, while doing your chemical reaction engineering, derivations of the rate equations and so on, or the mechanism of the reactions, we must be very careful about writing the chemical reaction. The general approach to the stoichiometry is that for solving any problem we must be very cautious about the units of the different concentration or different terms given for the particular problem. So, we should follow a general guidelines. One is clearly identify the goal, what you need to do, and then what are the units involved in that particular goal. Then the second thing is that determine what is given and the units. The second step you need to follow is what is given and what are their units. And then the third thing, use the conversion factor, their units, to convert what is given into what is desired. So, this conversion of the conversion factor has to be based on the particular units. So, we must be careful for while solving some particular problem in case of stoichiometry or any other problem when we are going to solve it. While solving reactions, we must know what is the limiting reactants for a particular reactions. Like if we consider potassium superoxide, KO2 is used for rebreathing gas mask to generate oxygen. The reactions happens KO2 4 mole reacts with 2 mole of liquid water and it forms 4 mole of KO is solid and 3 mole of oxygen. So, this KO2 potassium superoxide or potassium dioxide, it forms oxygen. So, its mask is used as a oxygen generator. Now, the problem is how many moles of oxygen can be produced from 0.5 mole of KO2 to and 0.2 mole of H2O. So, the given for this reactants 0.5 mole KO2 and 0.2 mole of H2O, and we have to find out which one is the limiting reactants, because the initial concentration for both the reactants are given. So, this is the reaction and these are given 0.5 mole of KO2 and 0.2 mole of H2O, and we have to find out the moles of oxygen produced. So, we have two starting materials, one is KO2 and another one is H2O, and we have to choose any one first. So, let us hide water. So, if we consider based on KO2 as the basis of the reactants, then we need to obtain the mole of oxygen produced if KO2 is the basis of the reaction. Now, how much is given? KO2 is 0.5 mole of KO2, and then as per the stoichiometry of the reactions, 4 mole of KO2 reacts with 2 mole of water produced 3 mole of oxygen. So, our moles of oxygen produced is 3 mole as per the stoichiometry, and that produced from 4 mole of KO2. So, if we write this 2, then this 4 mole KO2 and 0.5 more KO2, mole KO2 will cancelled out. Okay. And then we can calculate the mole of oxygen produced, that is 0.375 mole of oxygen. Now, if we consider the water as the basis instead of KO2, let us consider height KO2 and consider water as the basis. So, if we consider basis as water, then we can see that 0.2 mole of water is given initially, and then as per the stoichiometry 2 mole of water forms 3 mole of oxygen. So, produce 3 mole of oxygen from 2 mole of water. So, this mole water and mole water, they will cancelled out, and you will obtain 0.3 mole of oxygen. So, as we can see from this mole balance, we can see that the minimum oxygen produced from these two reactants is based on the water, that is 0.3 mole of oxygen. That means, this water is the limiting reactants, and so the limiting reactant is water over here for the production of oxygen, because this is the minimum quantity produced compared to based on KO2, and KO2 is the excess reactant. So, this way we can find out what is the limiting reactants. So, our general algorithm for any stoichiometry related problem would be, the idea is to how to find out the rate of reactions as a function of conversion in a particular reactant which will react and convert to products. The conversion, the extent of reactions or the conversion factor can be how to obtain, how to relate with the rate of reaction. So, the step to be followed, in the first step we should know the rate law, like minus R A is a function of concentration. As we have said earlier, minus, if it is second order reactions, it would be say minus R A would be K C S square. So, it is a concentration dependent term. So, this is the rate law. The second step would be the stoichiometry, how the concentration is related to conversion. So, concentration is a function of conversion, and third step would be combine these two to get minus R A is a function of conversion. So, these are the general procedure we need to follow. Now, we need to set up a stoichiometric table using species A as our basis of calculation in the following reactions. So, to find out the relation between rate of reactions with the conversion, we need to make a stoichiometric table. Stoichiometric table is nothing but it is a balance table for the conversion of reactants to products for a single reaction. So, suppose there is a reaction between A mole of A plus B mole of B, and it produced C mole of C plus D mole of D. From this, as we have earlier said, this would be minus R A by or R A by minus A, R B by minus B would be equal to R C by C would be equal to R D by D. So, from here we can write, if A is our basis of the calculation. So, this reaction we can write A plus B by A B to C by A C plus D by A D. So, this is written with per mole of A. This reactions is written per mole of A. Now, we will use the stoichiometric table to express the concentration as a function of conversion, and then we need to combine concentration as a function of x, that is the conversion, with appropriate rate law to obtain minus R A as a function of x. So, A is over here is the limiting reactant, as I have said already. So, now let us consider a batch system. So, this is the batch reactor, and where you have the content, all the content over here initially, and it is closed. At t is equal to 0, your condition is you have reactant Na naught. So, the reaction is A plus B to C plus D. So, this at t is equal to 0, the initial moles of all the reactants is reactants and products are given, that is Na naught, Nb naught, Nc naught and Nd naught. At t is equal to t, this is Na, the concentration of A is Na, concentration of B is Nb, concentration of C is Nc and concentration of D is Nd. So, this is batch reactor. Now, we have to do the mole balance, which is reacting over here. So, how much the reactants initially presents and how much A is reacting with B and how much product is produced. So, to do that, if we consider initially for the reactions, we had Na moles of A, Na naught, that is the initial concentration, and from the stoichiometry, as we can see that 1 mole of A is reacting and producing C and D. So, the conversion factor X, so Na naught X is consumed, reactant which is consumed. So, the remaining amount is Na naught minus Na naught into X. So, Na naught is the moles initially present and Na naught X is the moles of A consumed due to the chemical reactions. So, we will have Na would be Na naught minus Na naught X. Now, for every mole of A that reacts, B by A moles of B reacts. Therefore, the moles of B would be remaining as Nb would be equal to Nb naught minus B by A Na naught X. So, it would be Na naught into Nb naught by Na naught minus B by A x. Let theta b is the ratio of moles of B, initial mole of B divided by initial mole of A. So, this is theta b. Then we can write Nb would be equal to Na naught theta b minus B by A x. So, since Nb naught by Na naught is the ratio of the moles, so it is dimensionless term. So, theta b, which is for the simplification we can write this way. Similarly, we can write Nc is equal to Nc naught plus C by A Na naught x. This is Nc is the product which is produced, and how much moles of Nc is produced is C by A into Na naught x. This is based on the stoichiometry of the chemical reaction. And similar way, if we define theta c, which is Nc naught by Na naught, so it would be Na naught into theta c plus C by A into x. So, here theta c is Nc naught by Na naught. Similarly, we can write for the product D. Now, we need to develop the stoichiometric table. So, in the stoichiometric table, let us write species, initial and change of concentration, and what is the remaining concentration. So, initially we had the species A, which is concentration initially Na naught, and its change due to the chemical reaction is minus Na naught x, and then the amount remaining Na, which is Na naught minus Na naught x. For species B, initial concentration is Nb naught, then the change of concentration due to the chemical reaction, this mass is reacted, that is minus B by A Na naught x. So, Nb would be Nb naught minus B by A Na naught x. Now, for the product C, initial concentration was Nc naught, and the product which is produced due to the chemical reaction is C by A mole of Na naught x. So, Nc would be Nc naught plus C by A Na naught x, that is the product which is after a time of t. Similarly, for D we can write Nd naught is the initial concentration, D by A Na naught x, and the remaining one would be Nd naught plus D by A Na naught into x. So, for the product it is increasing from the initial concentration, for the reactants these are decreasing after the chemical reactions. So, that is why from the initial this is represented with the negative sign, and this is represented with the positive sign. Now, for the reaction to happen, if we have some inert gas or inert reactant present initially, so we need to also consider what would happen to that inert. So, initially suppose I is the inert and its initial concentration is Ni naught. So, because it is inert and not taking part into the chemical reaction, so it will not change its concentration. So, the whatever initially present of that inert will remain, that is Ni would be Ni naught. Now, if we make the total so this would be NT naught, and which we can just add them all of them Na naught plus Nb naught plus Nc naught plus Nd naught plus Ni naught. These are the initial concentration Nt, and then we can obtain the Nt from here, which is remaining. So, we can write Nt would be equal to Nt naught plus D by A plus C by A minus B by A minus 1 into Na naught x. So, this is the delta. So, this is can be called as delta, this coefficient is delta. So, this way we can develop the stoichiometric table. Now, our step 1 is minus R A, the rate of reactions is a function of concentration, and steps 2 is the concentration should be relations between concentration with the conversion. Now, if we consider concentration of A is the moles per unit volume, if we can write, so for this our minus R A is equal to K C square. Now, we need to convert concentration to conversion. First, we know the moles which is reacting. So, we need to write moles in terms of the concentration. So, if we divide with the volume of the reactants, so it will give the concentration. So, write concentration of A would be Na divided by the volume. So, this is per unit volume. So, then we can write Na is nothing but Na naught into 1 minus x divided by V. Similarly, we can write Cb would be equal to Nb by V, which is equal to Nb naught minus B by A into Na naught x divided by V. In case of product, that is Cc would be equal to Nc by V, which is Nc naught minus plus C by A into Na naught x divided by V. For D, that is Cd would be Nd by V, which is equal to Nd naught plus T by A Na naught x by V. Now, if we further simplify this term by defining theta b as Nb naught by Na naught, theta c is Nc naught by Na naught, and theta d is Nd naught by Na naught. So, if we define this theta term, then we can write Cb would be equal to Na naught into Nb naught by Na naught minus B by A x divided by V. So, this would be Na naught theta b minus B by A x by V. Similarly, we can write Cc would be equal to Na naught into theta c plus C by A x divided by V, and Cd would be equal to Na naught into theta d plus D by A x divided by V. So, this way we can write the concentration terms in terms of the conversion x. Now, if we consider constant volume batch reactor system, then our V would be V naught, that the initial volume, there is no change of the volume of the reactants or the system. So, we can then write Na would be Na naught divided by V. So, V we can substitute with V naught. So, Na naught by V naught, which is constant, we can write Ca naught into 1 minus x. Similarly, we can write Cb is Nb by V, Na naught by V naught into theta b minus B by A into x. So, which would be Ca naught theta b minus B by A x, and Cc we can write Nc by V, Na naught by V naught theta c plus B by A. This would be C by A into x. So, this would be Ca naught theta c into theta c plus C by A into x. So, this is for Cc. Now, for Cd also similar way we can write Nd by V, which is equal to Na naught by V naught theta d plus D by A into x, which is equal to Ca naught into theta d plus D by A into x. So, for constant volume batch reactor we can write the concentration term with the conversion and the initial concentration of the reactant A. Now, let us consider an example for the batch system. Consider the following elementary reactions with equilibrium constant K is 50 liter per mole and initial reactant concentration Ca naught is 0.5 mole per liter. The reactions is A to twice B and the rate of reactions is given as Ka into Ca minus Cb square by K. K is the equilibrium constant. We need to find out the equilibrium conversion Xc for the batch reactor. Now, our objective is to calculate Xc. We need to see what are given. So, K is given, that is 50 liter per mole, and the initial concentration Ca naught is given, which is 0.5 mole per liter. Now, we need to follow the steps. First step, we should know the relations dx dt would be equal to minus Ra V by Na naught. That is the Reid law, and the Reid law which is given over here is, so that is minus Ra has to be related with the concentration, that is minus Ra is equal to Ka Ca minus Kb Cb square, and then from here you can write minus Ra would be equal to Ka Ca minus Cb square by K. So, this K is nothing but the Ka by Kb. Now, we need to find the conversion Xc for a batch reactor, and this is the reaction. So, we need to obtain the stoichiometric table for the relations. So, Na, so A reactants is converting, its initial concentration is Na naught, and change would be Na naught x, and remaining would be Na naught into 1 minus x, x is the conversion. Now, for component B, if we look into this reaction stoichiometry, that 2 moles of B is produced. So, initially B was 0. So, only the A is present initially, there is no B into the system. So, B initial B is 0, and change would be twice Na naught x, and then the remaining would be twice Na naught x for B, which is the product. Now, the total NTO would be Na naught here initial, and NT would be, if you just add them, that is Na naught plus Na naught x. At equilibrium, Ra should be 0, as you know, and so if we write from the Reid equation, so this would be 0, and it at equilibrium we can write the concentration is CaE, that is the equilibrium concentration, and for B it is CBE. So, this would be CBE square by K. So, from here we can write Ke. So, this is nothing but Ke. So, from this relations at equilibrium, if we apply minus Ra would be 0 at equilibrium, then we can write this relation as this, the Reid equations we can write like this, and from here we can write Ke would be Cbe square by Cae. And Cae is nothing but Na by V, which is equal to Ca naught into 1 minus Xe, as V is for the constant volume system, V is V naught. So, Cae by V naught would be Ca naught into 1 minus Xe. So, Na naught by V naught would be Ca naught into 1 minus Xe, and Cbe would be equal to twice Ca naught Xe. So, now we obtained CAE, the equilibrium conversion in terms of Xc, and the equilibrium concentration in terms of Xc, and then equilibrium concentration of B in terms of Xc. Now at equilibrium, so this is the relation, and Ke is Cb square by Cae. From stoichiometry we have A2 twice B, and the volume is constant, V is equal to V naught, and then this is our stoichiometric table. So this is the overall process which we have done so far: equilibrium, stoichiometry, constant volume, and then we have obtained this. Now Na is Na naught into 1 minus x, Nb would be twice Na naught x, and V is V naught, and Ke is Cbe by Cae. So if we just divide with V naught, Nb by V naught would be twice Na naught by V naught into x. So this is nothing but Ca would be Ca naught 1 minus x, and from here Cb would be twice Ca naught into x. So now if we substitute this Cae and Cbe, we would obtain at equilibrium, this would be Xc and this would be Xc, and this is Be, this is Cae, that is at equilibrium. So if we substitute these two over here, so we would obtain, this is twice Ca naught Xc square divided by your Cae is Ca naught 1 minus Xc, which is written over here. So if we simplify, this would be 4 Ca naught Xc square divided by 1 minus Xc. Now if we just rearrange this relation, we will get Xc square divided by 1 minus Xc would be equal to Ke divided by 4 Ca naught. Now Ke is given is 50 liter per mole, and Ca naught is given 0.5 mole per liter. So if we substitute over here, this would be 50 divided by 4 into 0.5. So this would be 25. Now if we solve it for Xc, so you will get both positive and negative roots, but the conversions cannot be negative. So we have to take the positive one, and you will obtain, if you just do the calculations, we will obtain Xc, that is the equilibrium conversion, is 0.963. So this is how we can solve using the stoichiometric table. With a systematic approach, we can solve the different reactor problem very easily. In our next lecture, we will start with the flow system. So thank you for hearing this lecture, and we will continue our discussion in the next lecture.